When an atom enters a uniform, static magnetic field, its baseline energy state fractures into multiple distinct layers. This is the Zeeman effect. The split occurs because the atom possesses a magnetic dipole moment, which interacts directly with the external magnetic field to shift the atom's internal energy levels. We define this interaction through the classical perturbation Hamiltonian. The energy shift, H', equals the negative dot product of the atom's total magnetic moment, mu, and the applied magnetic field, B. Early quantum physicists assumed this total magnetic moment derived exclusively from the electron's orbital angular momentum, the physical motion of the charge around the nucleus. For atoms in spinless singlet states, this pure orbital model perfectly predicts what we call the normal Zeeman effect. The math yields a symmetrical, three-line spectral split. However, the vast majority of atomic spectra exhibit more complex, asymmetrical, and non-uniform splitting patterns. These irregular patterns, the anomalous Zeeman effect, demonstrated that treating the electron as a simple orbiting charge was mathematically insufficient to explain the observed energy states. To calculate the correct energy eigenvalues, the magnetic Hamiltonian required a complete mathematical reconstruction. The failure of the classical interaction model reveals that the electron possesses a second, non-classical source of magnetism that must be mathematically isolated. An electron carries two distinct sources of angular momentum, its orbital angular momentum, L, and its intrinsic quantum spin, S. In this vector space, plotting the total angular momentum, J, the orbital magnetic moment is a proportional function of the orbital angular momentum and the Bohr magneton. It points in the opposite direction due to the electron's negative charge. The spin magnetic moment introduces a new variable, the electron spin G factor, G sub s. This scalar stretches the resulting spin magnetic moment vector, making it disproportionately long compared to the spin angular momentum. Relativistic quantum theory requires this G factor to equal approximately 2. Because the spin G factor is 2, while the orbital G factor is effectively 1, the resulting magnetic moment vector points in a different direction than the total angular momentum vector. This spatial misalignment between total momentum and total magnetism is the mechanical root of the anomalous Zeeman effect. In a weak external magnetic field, internal spin-orbit coupling dominates. This causes both the orbital and spin vectors to precess rapidly around the total angular momentum vector, J. Since the total magnetic moment is rigidly misaligned from J, it is forced into a rapid precession around the central axis. This precession happens at a frequency far higher than the interaction with the external field. Consequently, the transverse components of that spinning magnetic moment average to 0. To find the measurable energy shift, we must isolate the time-averaged component of the magnetic moment that lies parallel to J. This mathematical operation is defined as a vector projection. The effective magnetic moment equals the dot product of the total magnetic moment and J, divided by the magnitude of J. Calculating this projection bridges the gap between rapid quantum precession and stable energy shifts. We now substitute our component definitions for the total magnetic moment back into the projection equation. Expanding the numerator requires us to evaluate two specific dot products, L.J and S.J. Since we do not know the specific angles between these vectors, we employ a standard vector magnitude identity to evaluate the dot products. Applying the identity to L.J allows us to rewrite it in terms of the squared magnitudes of J, L, and S. We execute the parallel expansion for S.J. In quantum mechanics, the squares of these angular momentum operators correspond to specific eigenvalues. We replace the squared vectors with the eigenvalue functions J times J plus 1, L times L plus 1, and S times S plus 1, scaled by h bar squared. Factoring this expanded equation back into our projection and isolating the variables collapses the geometry into a single scalar modifier. We define this output as the Landé G factor. The Landé G factor acts as the scalar coefficient that determines exactly how wide any specific energy level will split when exposed to a magnetic field. In a laboratory, applying a magnetic field to an atom causes a single glowing emission line to fracture into multiple unequally spaced thinner lines. Using the Landé framework, finding the exact intrinsic magnetic moment of the electron becomes an inverse algebraic problem grounded in experimental spectroscopy. We measure the precise frequency separation of these split spectral lines, such as the 3p to 3s transitions in sodium. Converting that frequency into energy provides the left side of our perturbation equation. Since we know the external magnetic field strength and the quantum numbers for the transition, we can extract the experimental Landé G value directly. We then rearrange the Landé formula to algebraically isolate the electron spin G factor. Inputting the experimental data into this inverted formula conclusively yields a spin G factor of approximately 2. Multiplying this value by the Bohr magneton and the spin quantum number mathematically defines the intrinsic magnetic moment. While modern metrology uses Penning traps and QED to measure this to parts per trillion precision, this spectroscopic derivation is the foundational proof. By observing the anomalous splitting of spectral lines and rigorously projecting the quantum vectors, the Zeeman effect provides the mathematical proof for the existence of electron spin.